Hello, everyone. My name is Chenxu Niu. I'm from Texas Tech University. Today, I'm going to talk about semantic search and natural language query over HDF5. In this project, I have been working with Dr. Wei Zhang from Lawrence Berkeley Natural Lab and Dr. Survana from Ohio State University, and my advisor, Dr. Yu Chen from Texas Tech. This is the overview of today's talk. First, I will review the traditional scientific data management and querying methods. Then I will talk about my proposed static query method for HDF5 files. And then I will talk about the emerging large language models and the related applications. And at last, I will propose a novel large language model-based metadata search engine over HDF5. So first is many scientific applications will generate and store the massive amounts of experimental, observational, and simulation data in self-describing file formats such as the HDF5 in many domains like the environmental science, the astronomy, bioinformatics, and physics. So to fully leverage the data potential, we need to figure out a better way to manage and to query this data set. So this method should have some features. First of all, you need to handle this large-scale scientific data efficiently, and you need to organize the data for easy access and retrieval. And then you need to accelerate the data discovery and analysis. And then you need to reduce the time spent on manual data searches. So here I reviewed the traditional metadata search method in the last 50 years. So you can see it's a timeline of the scientific data management and the methods. So there are many useful tools here like BMM, and like Target, Somata, and Impress, and Mix. Just mention the Mix, right? So yeah. And next is about based on the storage technique, it can be categorized into 3 different kinds of methods. So first one is pure dataset scanning method. You can see it will only scan the scientific files and then store the metadata in pure key value pair patterns. And the second kind of is database powered method. It relies on the relational database. It stores the metadata into the relational database and rely on the query functionalities of this database. The last one is index-based methods. It will build multiple indexes on the HDF5 files and then query based on this metadata indexes. And I have shown some examples of these 3 different kind of methods. You can see Meta, Kiwi, BIMM, Impress, and Target, and Mix here. And but based on the query types they support, we can categorize them into two different kinds of methods, like the circle search, because they rely on the relational database, so they can use the query functionalities of the relational database, and the rest of them they use the keyword search, or we can call it like lexical match method, and they also can use the extended keyword search, such as the suffix, prefix, and key value search. A typical example is the mix, and the last one, edomix. Dr. Wei Zhang mentioned the last one, right? So, but they all have one drawback. So they share the same drawbacks. So they only support keyword search, or we can call it like the lexical match. So here is why do we need the semantic search over HDF5 files? What is the drawback of the keyword search? So first of all, they can only like use the lexical match or partial lexical match. It cannot understand the meaning of your query intent, or they can't read the context So, but the semantic search can understand the context and meaning of your query input and the metadata attributes. So, suppose we have an example here. The query input would be velocity and the speed here. So the keyword and the lexical can only match the metadata attributes contains the velocity or speed, right? And you can only find the related files with the attributes in with the velocity and method speed. But if you use some semantic search, when you search for the velocity, you can find the speed, velocity, and rate. So if you can have a richer set of HDF5 files. So how can we move beyond from this lexical search of HDF5 to the semantic search? So what is the gap here? And how can we bridge the gap? So we need to bridge the gap between the lexical search and semantic search. First of all, we need to represent the data in a way that captures its meaning, right? And after that, we need to use, because in some other domains, they use like embeddings to transform the word into continuous vector spaces. For example, some word-to-vec, globe, and fast text, they all can transform the word into some vectors. Then you can use some like cosine similarity to measure the distance between these vectors to measure the semantics of the words. So, but how to apply this technique in our domain? So the first question is how to capture the embeddings of key-value pairs instead of words. And the second one is how to measure the semantic similarity between metadata and query input. So, and based on these two challenges, we have two papers. The first one we published, we proposed a method called key-value-to-vec, which means key-value pairs to vec. And the second one we proposed a method called PSQS, parallel semantic query service, to answer the second question. So I will introduce it. The first one is key-value-to-vec. The first part of this method is that we need to define a pre-trained dictionary for key-value pairs. So first of all, we use the dictionary from the word-to-vec. We can find distributed representations of common words. They can be generated from like word-to-vec or globe or fast text. And then we need to enlarge the dictionary to include the terms in key-value pairs because we have like many special terms in metadata attributes. And then we apply retrofitting techniques with these properties. And after that, we can propose our way to like have a distributed representations for key-value pairs. We can compose the vectors from words into one single vector to represent a key-value pair. And then here we applied our RNN called recurrent neural networks with a long short-term memory. So here's the diagram of key-value-to-vec and the word-to-vec. So the first half is word-to-vec. You can see it. They are used to capture the relationships between two words, and you can use the hidden matrix to like keep capturing different words, and then you can have like a continuous vector space to represent one word. And in our method, we use two like parallel system. So one is used to capture the keys from the attributes, and the second one is about the values from the attributes. Then we can use the RNN to compose them together into one single vector. And based on it, we can propose our second one, our second method. We call it like PSQS, parallel semantic query service. So in this figure, you see the last half is about the key-value-to-vec, right? So first of all, we need to build the index. We call it the semantic index. So here, each semantic attribute, we can map them into different key-value pairs, and it can be mapped into a semantic vector with keyword pair, with keyword rag, and after that we can create the semantic indexes. So they are clusters of semantic vectors, and then we can calculate the choice of the semantic cluster to represent each cluster. And after that, how to process the query. So here we can convert the queries. First, we can convert the queries into vectors because they can convert the keyword pairs. They can also convert like query input, the keywords into vectors. And after that, we can try to match the vector to calculate the distance between the vectors. So we use the cosine similarity to calculate the distance between the query vector and the index the vectors. And then we can retrieve the corresponding object paths. And here is the results of our method compared to some other methods. We compared it with the mix globe and the MongoDB based method. So we can see from the query case and the recall, we can get the results here. We have like over 15% improvement, and for compared with the globe, we can have a 13% improvement. For the recall, we can have like over 17% improvement. But now you see a lot of large language models have been proposed, right? So we can, it means we can use more features of them to build a natural language query method. This is a figure of like the large language models of the last 5 years, right? So we can see many large language models have been released, published by the big companies like Google and Meta, like OpenAI. Right? So like GPT-3 and the Llama and the Bard, GPT-4o, and actually many large language models are fine-tuned and built based on these basic models. So we can also build our method on it. So here is the diagram of our new engine. We call it large language model. This is the metadata search engine LMSE for HDF5. So here, the users can issue the input in natural language, and then it can be converted into embeddings and could be the input of the search engine, and the search engine will process it and then answer it in natural language. So, and I will show you a demo later. But what is behind the search engine? So here you can see we have 3 important components inside the search engine. The first one is we need to extract the metadata from HDF5 files. And after that, we need to like design some prompts that can be used to help pre-train and fine-tune the large language models. In our experiments, we use Llama 3 and GPT 3.5 in our experiments. And the last one is very important. So we need to define metadata structure recognition methods. It is used to like how to read the metadata structures and how to let the model to read your metadata attributes. And after that, we can it is our search engine. Here is I want to show you a demo query. Here is a query. So there are 6 queries here. So how many files in total, and the ownership of the second files. So please make sure all the words are not doesn't exist in the metadata attributes. They will understand it and give you the results. Like let me show you one by one. So here is our engine. So here is just a query test. So I just run it in Jupyter Notebook, and here is the first query. So here the query is how many files in total. Then it will the search engine will understand and then help you to print the metadata instructions. Then it will print like a Python function like length metadata, and then it will output metadata output is 10 because it's only a demo program, so this folder only have 10 HDF5 files. So, and then you see the execution time is 0.5 seconds, and after that is the ownership. So if we want to find the ownership of the second file here, you can see the metadata instruction is a metadata, then it's a file name, and then author, right? It's not the ownership because it can understand the semantics between the ownership and the author, and then it will output the metadata, right? So the the third one is the radius range. So it's a number, right? It's a radius range, and after that is which file is generated older than 2020. So here you can see the search engine can translate it into like if the data year is smaller than 2020, right? You can see here the output is right, is correct, and list all the authors of the files. It can find all the authors because it can extract all the metadata into structured format and then print out all the authors. And the last one, they can have a radius range greater than 30 to 40, it is right. So it's just a quick demo of this engine. And this is the experiment of our search engine. So the matrix we want to evaluate is for now, it's the accuracy and the execution time. So we compare our search engine with Llama 3 and Code Llama. For the Llama 3, it's just a basic model. For Code Llama, it's used to generate the code and then use the code to query your metadata. And you see, we have two different versions of our metadata search engine. For the API version, we build it based on the GPT 3.5 API, and for the local version, we build our metadata search engine based on the Llama 3, local Llama 3, and we issued like 107 queries, and then we check the result manually. Then you can see the result for the accuracy. Llama 3 only print out the 21 correct answer, and the Code Llama is 16 because it cannot understand the metadata structure correctly. That's why it's smaller. So, but our search engine can have like over 100. There are only 3 wrong answers. And for the execution time, the Llama 3 and the red line is used to represent the execution time. So you see our search engine is even smaller than Llama 3 and Code Llama, and the local version is the best one. It's very efficient. Okay, so it's a summary of our future work. So we developed KV2Vec for capturing the semantics and the embeddings for the key-value pairs, and we also implement the PSQS for semantic querying over HDF5 files. And after that, we demonstrate the significant improvements in query accuracy and recall compared to some existing methods. And it's our ongoing project. We are building large language model-based metadata search engine to enhance the semantic search capabilities for HDF5 files. And in the near future, we want to continue to fine-tune and optimize the data for higher accuracy and to ensure it can handle large-scale data sets, and it can support more complex queries. And the last one, we want to compare it with some different other solutions. Okay, so here is the QR code of our lab and the code in my GitHub repo. And I want to express my special thanks to Dr. Wei Zhang. He helped me a lot and make a lot of contribution in this project. Thank you guys.
Hi, So I have a use case where we're used for like information. Right? So is this something I can switch on if I need like for a person and I just play it? I'm just curious about some of the integrated.
For that, we haven't published the search engine, so but we can publish maybe in the next 2 months. So and you can build it in servers, and we plan to like maybe make it like a Docker version that you just download and use it. Yeah, it's very simple. Yeah.
Yeah, I mean, I can write the file to it. It's just a short version, but no, that'll be great.
Okay. Okay. Right. Thank you. Yeah.
The performance difference when you compare to the Llama with your method, is the main difference really in the embedding, or what are other explanations for this difference in performance?
Oh, the performance because this search engine is especially built for the metadata structure. So it's like the metadata recognition is like a pre-built or pre-processing method, pre-processing. So that's why it's very efficient. And if you use Llama 3 or code Llama, it will learn it again and again. You need to use the prompt to teach them to learn the metadata. But in this in our metadata search engine, we have already taught the model to learn it. That's why I think it's more efficient. Yeah. Did that answer your question?
Follow. Yeah, yeah. We'll,
Okay. All right. Thank you.